Hi, I am Lopamudrashen. Welcome back to my channel after a long break. So today I will continue with tunnel diode topic. So in my previous class we will learn about what is tunnel diode and what are its characteristic properties, right? So continue with tunnel diode or tunnel devices. Okay. Today we will discuss about the energy band diagram of the tunnel diode. Next we discuss about what is the volt ampere characteristics of a tunnel diode. Okay. So this is the energy band diagram of tunnel diode, right? So this side is N plus region and this side is P plus region. Why this is represented as N plus region and P plus region? Because we know a tunnel diode consists of a simple PN junction in which both P side and N sides are heavily doped with impurities. That means the both sides are degenerated. Okay, that's why we get a sharp transition. Okay, so this is represented by N plus region because it is heavily doped with impurities. That means this is degenerated, and this side is also represented as P plus region because this side is also heavily doped with impurities. This is also degenerated P plus region. So these two regions are represented as N plus region and P plus region. And here is the difference between one simple PN diode and one tunnel diode. So this is the energy band diagram of a tunnel diode in thermal equilibrium condition. Because of the high doping, that means heavily doped with impurities, which is called high doping, the Fermi levels are located within the allowed band. Okay. Since the doping is very high, the Fermi level lies within the band of the semiconductor at absolute zero temperature. In the absence of any bias voltage, the Fermi level EF, which is represented as EF, in N side it is represented as an EFN, and in the P side it is represented as EFP. So the Fermi level is constant throughout the system at when we does not applied any bias voltage, right? So this is the thermal equilibrium condition. The Fermi level EF is constant at the junction at thermal equilibrium condition. Since the Fermi level is the highest occupied energy level, no current can flow through the junction. Okay. And the amount of degeneracy is Vp dash and Vn dash. Vn dash is the represented in N side degeneracy voltage, and the P side degeneracy voltage is represented as Vp dash, which is typically a few kT by Q, where K is the Boltzmann constant, T is the temperature, and Q is the electronic charge. Okay, and the depletion layer, this depletion region is of the order of 10 nanometer or less than 10 nanometer, which is very narrow region. Okay, than the conventional simple p-n junction diode. So this is the basic difference between a simple p-n junction diode and a tunnel diode, and this is the energy band diagram of tunnel diode in thermal equilibrium condition. Okay. So what is the static characteristics or static current voltage characteristics of tunnel diode? This is the static current voltage characteristics of a typical tunnel diode. Okay. First of all, we discuss about what will happen when we apply a reverse bias voltage across a tunnel diode. What does it mean? It means we applied negative bias at P side with respect to the N side, and the current increased monotonically. Okay. And in the forward direction, that means in this direction, the current increases to a maximum value which is called peak current, and we get this peak current at the maximum voltage, and this voltage is called peak voltage Vp. Then the current value is decreases to a minimum value, that is IV, and this voltage and this current is called valley current, and the respective voltage is called the valley voltage VV. So this is the forward direction characteristic curve, that first of all the current will increases to a maximum point, and then the current will start decreases to the valley point. Okay, so this is the static current voltage characteristics of a tunnel diode. Okay, so this is the static characteristics or static current voltage characteristics of a typical tunnel diode, right? And this is the forward direction, biasing current, and this is the reverse biasing current. If we divide these static characteristics, we get the three resultant current components. One is band-to-band tunneling current, another is excess current, and the other one is diffusion current. So band-to-band tunneling current is represented by this dashed portion. The diffusion current is represented by this dotted line, and the excess current is represented by this dashed line. So these are the three current component of a static characteristics of a typical tunnel diode. We will discuss one by one. Okay. So the first energy band diagram of tunnel diode, and from this energy band diagram how we get the static characteristic curve we will show here. Okay. So this is the energy band diagram, and this is the corresponding static curve of a tunnel diode. This is also energy band diagram. First, this case we will discuss, and from this case we will saw how we get this curve, right? So this is the figure 1. Here we saw this is the Fermi level, this dotted line is the Fermi level. This side is N plus region and this side is P plus region. So this side Fermi level is called EFN and this side Fermi level is called EFP. And at thermal equilibrium condition, when we applied no bias voltage. The Fermi level is throughout constant throughout the junction. Okay. So we saw here that the Fermi levels are within the allowed bands of the semiconductor, right? So the Fermi level at thermal equilibrium condition lies within the allowed band of the semiconductor, and it is constant across the junction. Above the Fermi level, there are no field state on either side of the junction, and below the Fermi level, there are no empty state available on either side of the junction. Hence, the net tunneling currents is 0 when we applied 0 voltage, and this is represented by this dotted portion in this curve. This is the first portion of the curve. When we applied no bias voltage, the Fermi level is constant across the junction at thermal equilibrium condition, and above the Fermi level there are no field state electrons, that means on either side of the junction, and below the Fermi level there are no empty state, that means holes, available on either side of the junction. Hence, the net tunneling currents at 0 applied voltage is 0, and this is represented by this dotted portion. Okay, so this is the energy band diagram, and from this energy band diagram we get this point in the static characteristic curve, right? Now we consider the second figure. This is figure 2. When a voltage is applied across the tunnel diode. When a voltage is applied across the tunnel diode, the electrons may tunnel from the conduction band to the valence band or from valence band to the conduction band. And what are the necessary conditions for this tunneling? First of all, the occupied energy states exist on the side from which the electron can tunnel. The second condition is unoccupied energy state must be exist at the same energy level on the side to which the electron can tunnel. And the number 3 condition is the tunneling potential barrier height is low and the barrier width is small enough that there is a finite tunneling probability. And the last condition is the momentum is conserved in the tunneling process. So these 4 are the necessary conditions for tunneling one electron from conduction band to valence band, when this electron may tunnel from the conduction band to valence band or vice versa. So this is the picture, second picture, and from this second picture we will get this portion, this increasing portion, right? So this is the tunnel current when the electrons, when we applied a voltage, the electrons may tunnel from the conduction band to the valence band and we get a tunnel current, and that will increase when we increase the bias voltage, and this current will linearly increases at some maximum point which is called peak current. Okay, so this is the peak current and the corresponding voltage is called peak voltage, that is represented as Vp, and this peak current is represented as Ip. So this linearly increasing portion is represented as that electrons may tunnel from conduction band to valence band or valence band to conduction band, right? So this portion here we draw from this energy band diagram. Next we saw the figure 3. This is the figure 3. When a forward voltage is applied, there must be exist a common band of energies in which there are field states on the N side and unoccupied state on the P side. Field state on the N side and these are the unoccupied state in the P side. The electrons can thus tunnel from N side to P side and the energy is conserved, right? When the forward voltage is further increased, this band of common energies decreases, and this decreasing portion, that means the current will also decreases, and that's why we get this negative slope region of the current. That means we get from maximum point to valley current, maximum current to valley current, and this negative slope is we will get from this energy band diagram. So now we saw the valley current and the corresponding voltage is valley voltage, right? So in this portion we also understood from this figure, right? Next, if forward voltage is applied that the bands are uncrossed, that means the edge of the N-type conduction band is exactly opposite to the top of the P-type valence band, there are no available states opposite to the field states. Thus at this point the tunneling current can no longer flow, right? Then we will still further increases the voltage and then we get the normal diffusion current, and this is the diffusion current. In this portion we cannot get any tunneling current, we get diffusion current, because when we further increase the forward voltage the bands are uncrossed, that is the edge of the N-type conduction band is exactly opposite to the top of the P-type valence band, and there are no available states opposite to the field state. Thus at this point the tunneling current are no longer flow and we get here diffusion current, and the excess current start to dominate the diffusion current. So this portion is expressed by this energy band diagram, and this current portion is called the diffusion current. This is not tunneling current, this is diffusion current, right? In next picture we saw here this energy diagram. This energy band diagram means this is the reverse bias condition. When we apply reverse voltage at the PN junction or simple PN tunnel diode P plus and N plus region, when we applied the reverse bias voltage, what we get? this portion we get where the current increases monotonically. When the junction is reverse biased, the Fermi level in the P side goes up. The Fermi level in the P side goes up relative to that in the N side. And the electrons in the valence band of the P side are separated by a thin barrier represented by the depletion region. This region is called the depletion region. From the available states in the conduction band of the N side, hence the electrons can tunnel from the valence band of the P side to the conduction band of the N side. Right? The greater the reverse bias, the large the number of electrons that find available unoccupied state at the energy on the other side of the thin barrier. Consequently, the tunnel current increases. When we increase the reverse bias, the large the number of electrons that find the available unoccupied states of the at the energy on the other side of the thin barrier, and consequently we get the tunnel current increases with the increasing reverse bias, and this portion is represented as this, and here we saw the current will increases monotonically, right? So these are the energy band diagram, and from this energy band diagram we get this static characteristic curve, right? I hope you understand this topic. Thank you. Thank you. If you like my video then please like, share and subscribe my channel. फिर मिलते हैं एक नई वीडियो के साथ. Thank you.